Good afternoon, everyone. Welcome to our Reading Online Sport Economics seminar. We're very pleased to have presenting today Marius Oetting from the University of Bielefeld, Germany, presenting exploratory analysis of in-game betting dynamics. We're going to follow the usual format this afternoon. So if you're able to keep your microphones on mute, and it's also best if you're not sharing your video as well, although it's fantastic to see so many faces at the start of the meeting. Just in case people struggle with bandwidth and so on, it's best if you keep your microphones on mute and your cameras off for the duration of the talk. Marius will have about an hour in which to talk, and there'll be plenty of time for Q&A at the end. If you're able to see the chat function in here, please do make use of it. Please do stick questions in there and comments in there if you want to. I will endeavour to give Marius the 60 minutes just to talk, but if there is important questions of clarification, we will reserve the right to stop Marius in full track. But if there are none of those, Marius will go through 60 minutes and there'll be plenty of time for Q&A at the end. So without any further delay, Marius, I'm going to hand over to you, and please do share your screen and take away your talk.
Okay, yeah, then I will share my slides here and make it full screen. Can you see it?
Yep, perfect.
Okay, great. Yeah, then hello everyone. And yeah, James, thank you for the kind introduction here, and thank you for setting up this nice seminar series. And yeah, thanks for having me here today. So my talk is about an exploratory analysis of in-game betting dynamics. And this is joint work with Ruven Michels, Christian Deutscher, and Roland Langrock. We're all from Bielefeld University in Germany. And yeah, I work here as a postdoc within this project, which is funded by the German Research Foundation. Okay, so as you can see from the title, this talk here will be about betting markets, and I will give you a brief overview of betting markets in general here at the beginning. So you see here 3 different headlines from different newspaper articles, and here in the first one we see some numbers about betting markets in general. So we see that betting markets also suffered from, or betting companies suffered from the corona pandemic in 2020. So every year there are of course several official numbers reported regarding the betting markets, but here one number which is of huge interest is the so-called gross gaming revenue. So this is simply the money bookmakers win from their clients. And in 2019, this was estimated as about 100 billion euro, but due to the corona pandemic, we observe a drop here of 23%. So in 2020, this value was estimated as 75 billion euro, which of course is still lots of money, which suggests that betting markets in Europe are very large and highly liquid. And of course, this doesn't come without consequences. So the betting industry is linked to different sports and of course also to football. So for example, if you think of shirt sponsorships or advertising on TV, that's where you usually see lots of names of different betting companies. And however, this does also not come without a problem, because one headline here says betting in dressing rooms is quite common. So this is of course a problem if players bet on matches where they take place, or matches from players they know very well. So this kind of could be related then to, or could lead to match fixing, which of course is a huge problem. Okay, so to introduce you a bit more to betting markets in general, I'll present some more numbers. So on the previous slide, we have seen this gross gaming revenue, or short just GGR, and this has grown very rapidly in the past decades. So in year 2000, this was estimated as 6 billion euro. In 2010, it was 19 billion euro, and yeah, in 2019, so before the corona pandemic, it was about 100 billion euro. So we see that there's a very strong growth of sports betting markets in general. And next to this rise of sports betting, there's also a rise of so-called in-game betting. So in general, in betting markets, you can split these betting markets into 2 parts. There's a pre-game betting market where you're allowed to place your bets before a match starts. and you can also place your bets during a match. This is often called in-game betting or live betting. And in the last years, this in-game betting became more and more popular, so that nowadays in-game betting accounts for about 75% of the overall volume. So, I mean, that means if we have like very highly liquid betting markets, and if most of these money is like generated in the in-game betting market, then bets have to be placed like in almost every second in a match. And just to give you some intuition how this could look like, I will here show you some of our data. So this is one example time series here from our data set. I will explain the data a bit more in a minute. But for now, what we can see here are the stakes placed on Borussia Dortmund in the German Classico, how the media labeled it, Borussia Dortmund against Bayern Munich. This match here has taken place in November 2018. And what I have to say here is that, of course, you see a y-axis here, which is the stake, but you can't make any sense here out of these numbers, because these numbers, they were transformed before we got the data from the bookmaker, so you can't make sense out of these absolute values here, but we can, of course, compare these different stakes which were placed here in the match. And what we see here is that, so one black line here refers to all bets which were placed in a given second, and what we see here is that there are lots of black lines. So there are only very few instances in this match where no bets have been placed. So we see that there's a betting behavior, or that people place their bets like all over the match. Okay, so if you see such kind of data, you may already have like different research questions in mind, which one could analyze using such data. But here in this talk, I want to investigate the drivers of betting volumes. And a bit related is the question, how do markets respond to news? And this is something which has been investigated in finance several times. So for example, here the letter mentioned paper, they investigate the effect of news regarding the corona pandemic on financial markets. However, one drawback when you investigate like the effect of news in financial markets is that there's no clear time point when this news appears like for the first time. And this is a bit different, of course, in betting markets, because, for example, if we consider football betting here, news are then simply, for example, goals. And for goals, we have a very precise time point. So for each goal, we have the exact minute and also the exact second when a goal was scored. So we have a very precise time point here. And there are indeed some previous studies who already investigate in-game betting markets, mostly with a focus on market inefficiencies. So there's, of course, also one paper here by our host, by James Reade, published in 2014. So these papers, they mainly focus on investigating betting market inefficiencies after, for example, goals were scored. Here in this talk, we investigate not the odds, but the betting volumes. So we want to investigate what drivers of betting volumes there are. And for that, we first have, of course, to find like a good statistical model to model the stakes which are placed during a match. And with regard to news, so maybe we can make a bit more sense out of the plot I showed you in the beginning with some more information about the match. So this red dashed lines here, they indicate goals which were scored by Bayern Munich, and the yellow dashed lines, they indicate goals scored by Borussia Dortmund. And these black dashed lines, they indicate the halftime. And what we see here is, I mean, these are the bets placed on Borussia Dortmund, that after they score a goal here or here, so after they score the first or second goal, the betting volume tends a bit to increase compared to the minutes before the goal. We can, of course, also analyze not only the bets placed on Borussia Dortmund in that match, but also the bets placed on Bayern Munich. In the same match, we observe a similar dynamics. However, the average stakes which are placed on Bayern Munich, if you look at the y-axis, seem to be a bit lower here. Okay, I will now talk a bit more about the data set. I mean, I've shown you like 2 example time series here, but I will give you a bit more details regarding our data now. So the data we use here, the data set includes all betting volumes which were placed during a match in Bundesliga matches in the last season, or the last full season before the Corona pandemic, which is the season 2018-19. And this data set was provided by a large European bookmaker. And here in our data set, not only online betting is included, but also bets which were placed in betting shops. And the resolution is fairly high, so we have a second-by-second data set. So for each second, we know the amount of money which was placed on some team or whatever. But as I said in the beginning, the stakes you see here, these are not the true stakes. These were transformed before we got the data. And to make the analysis here a bit easier, we aggregated the data into intervals of 15 seconds. So that means that for one match, we have about 420 observations per match. And we consider here the bets on the home and on the away team separately. So similar as I've shown you on one of the previous slides, where we had these two time series, one for the bets on Bayern Munich, one for bets on Borussia Dortmund. We do not consider bets on the draw here so far. These are not included here. And then we end up with 306 matches, so all Bundesliga matches in season 2018-2019. And for each match, we have then two time series, one for the bets on the home team, one for the bets on the away team, so 612 time series. And if you multiply these 612 by 420, we end up with about 250,000 observations. And all the work we've done so far, and we will hopefully do in the future regarding this data set here, is funded by the German Research Foundation. Okay, so before we go on and model the stakes, I want to show you some more patterns here, which we see in the data, because I mean, as you can maybe imagine from a football match, there are different dynamics in a football match, or different courses a football match can take, and the same also applies to the betting markets, or the in-game betting markets for these matches. So here we see the bets which are placed on Augsburg in a match against Wolfsburg, which was played in May 2019. And here the yellow dashed lines refers to the goals scored by the opponent. So here in this case, we are looking at the bets of Augsburg, so the opponent here would be Wolfsburg. So the yellow dashed lines are goals scored by Wolfsburg. The green dashed line is the goal here scored by the team which we're analyzing here, so Augsburg. And in the beginning, we see that there is the quite active betting market here. Lots of bets here placed on Augsburg. Then Wolfsburg scores their first goal. Even before the halftime, they scored two more goals. And then, of course, the betting behavior, or the market activity, like decreases. So here then at halftime we see some bets on Augsburg, but at the beginning of the second half, Wolfsburg scores another 3 goals. So, and then we do not observe, or almost no bets for the rest of the match on Augsburg to win. So this is like a fairly extreme example where a match was like very early decided. Of course, we have also some different matches here. So if we look at the match on the top right, for example, these are the bets placed on Borussia Dortmund in a match against Hertha Berlin. And we see here that this is a bit of a hard-fought competition. So first Berlin scores a goal, then Dortmund scores a goal, then again Berlin, and then it's Dortmund again. So we see here that bets are placed like all the time. A similar pattern we see here in the bottom left plot, where the bets on Augsburg are shown in a match against Leverkusen. We see here that there was just one goal scored here at the end of the match. So this match was even like most of the time. And we here see that we also have bets like in almost every second here in this match. And we see here also, but also in the other plots, that these matches, or these, not these matches, these stakes, they seem to occur in some periods. So here we have a period around 4 p.m. where the betting volumes are a bit higher. After that, we have a period where the betting volumes are a bit lower. And then again, we have a period where we observe, again, rather high betting volumes. So this is something I will talk a bit more in a minute, and this is also something which we have to keep in mind. On the last plot here, these are the bets on Stuttgart in a match against Bayern Munich. And here we see, okay, Bayern Munich, they score the goal very early. So they're leading here, and we observe only very few bets or low stakes bets on Stuttgart. But then Stuttgart, they score a goal, and after that the market activity here increases, and we observe lots of bets and also bit higher bets here on Stuttgart. But then at the end of the match, Stuttgart receives a goal. So Bayern Munich scores a goal, Bayern Munich scores another goal, and then of course if Bayern Munich is leading by 2 goals, almost at the end of the match, we observe only very few bets here placed on Stuttgart. Okay, so these are just different patterns we see in the data, different dynamics, which we somehow all have to account for when formulating our model. So I will briefly summarize them. So what kind of patterns have we seen here, have we found in the data? So we have seen that the stakes are on average a bit higher for teams of higher quality. We observe that these high and low stakes are occurring somehow in clusters, so that there are clusters of high and of low stakes. And we also see some effects if a match is like almost decided, because if a match is like almost over, then very few bets are placed, and if some bets are placed, then the stakes are often very low. What we also see, maybe I will go back one slide here, you see this maybe here best in the figure on the top right, is that if a goal was scored, so if you look at these dashed lines, you see right after these dashed lines, we do not observe any bets. And this is simply because the bookmaker then adjusts the odds, and nobody is able to place a bet. So betting is simply permitted. Then the markets are closed. The bookmaker adjusts their odds, and the market is closed for maybe some seconds or maybe 1 or 2 minutes. And we also further saw that these stakes that they vary a bit with the day of the week. Okay, so to incorporate these patterns we see in the data, we need mainly two covariates here. One covariate is a proxy for the uncertainty of outcome, or the current uncertainty of outcome at time point t, and of course also a proxy for the quality of a team. And with the latter one, with the quality of the team, this is maybe a bit more easy here. So we use here the market value simply as a proxy for a team's quality. These can be simply found online, and the higher the market value, the higher is on average the quality of a team. For the uncertainty of outcome, we make use of betting odds here. So our data set not only covers the volumes which were placed on a given match, but also the odds at each time point t. So based on these betting odds at each second, we can simply calculate the implied winning probabilities for both teams. And based on that, we calculated the Gini coefficient. And the Gini coefficient is then a continuous measure which ranges between 0 and 1, where 0 means that a match is very close, so both teams have equal winning probabilities, and the Gini equal to 1 would mean that there's like a very clear favorite. So for example, if Bayern Munich is leading by 3 goals 10 minutes before the match ends, then this would refer to a Gini equal to 1. Okay, so we can see some descriptors here around these covariates. So the odds are then incorporated here in the Gini coefficient, which ranges between 0 and almost 1. Of course, we also see a high variance here in the odds. And the betting odds, the market value here is measured in million euro. And the open market here, this is simply a dummy variable, which indicates whether the market is open at a given interval or not. And we see here that in 90% of all intervals, the market is open. What you can see not here from the table, which is just here noted as a further bullet point, is that if the market is open, so in all intervals where the market is open, in 7% of these intervals, no bets are placed. So this may refer then to matches which are like almost decided, or may refer to situations at the end of a match. We will focus on that also later. Okay, so based on these descriptives, I will now come to formulating a statistical model to model these stakes here placed in in-game betting markets. And at first we have to choose, of course, a distribution for the stakes. And since the stakes, which are just denoted here by y, the stakes are most of the time greater than 0. Sometimes they are also equal to 0. So assuming a normal distribution here would not be appropriate. And since we have a continuous valued response, so the stakes are continuous valued and greater than 0, we have chosen the gamma distribution here. But as the standard gamma distribution does not allow for values equal to 0, we use here the 0 adjusted gamma distribution. And in addition to that, you may remember from the gamma distribution that there are some different parameterizations. So for example, there's one parameterization with a scale and a shape parameter, and these parameters, they are not that straightforward or not that easy to interpret. So we use a different parameterization here, which was proposed here in this book, which is the 0 adjusted gamma distribution where you simply have a mu, which is mu, which is the mean, sigma, which is the standard deviation, and pi, which is the probability that we observe a stake equal to 0. And then we can simply use this function f here. So this means that if we observe a value of 0, so if we observe a stake equal to 0, this occurs with probability pi, and with probability 1 minus pi, if the stakes are greater than 0, then they are assumed here to follow the gamma distribution. Okay, so what else do we have to take into account when modeling the stakes? So, I mean, what we have here is, of course, a clear time series data. And what we also see, and what I highlighted or tried to highlight a bit in the beginning, is that we see different periods here of betting activity. So, for example, here around 7 p.m., we see that there are stakes placed which are rather high. So this would maybe here refer to a period where the market is rather active. At 7:15, things are a bit different. Here the stakes which are placed here, they are rather low. So we observe that these that there are kind of different periods. So periods where the stakes are rather high and periods where the stakes are rather low. And here to model this, we use some kind of state space modeling. So we here assume that the market's activity level drives the underlying stakes. So that the stakes, that they depend, of course, on some covariates, but that they also depend on the activity level of the market. And the activity level of the market is, of course, something which we cannot observe. However, if we think of that, and if you think of like the most easy translation into a model, this would refer to a model with two latent states. So where we have two states of market activity, which would maybe refer to an active market and a non-active market. And if we look at the time series again, so here at 7:15, this would maybe refer to a non-active market, and here maybe at around 8 p.m. this would refer to a more active market. Okay, so how does that look like then here? So this is like a figure here showing the dependent structure of our model. So we have these two sequences. We have the stakes here, which are denoted by Y, and we have the unobserved level of market activity, which is denoted here by G. And the stakes are assumed to be driven by this underlying unobserved level of market activity. And we assume that the market activity level at time point t, so at interval t, depends here on the market activity level at time point t minus 1. And what we have to decide here is how many states of market activity do we want. On the previous slide, I said, okay, in the most simple case, we would have two states. We would have a non-active and an active market. But one could also say, okay, I would say there are three states where we have maybe a non-active market, a medium active market, and a highly active market. And you could maybe also go for 4 states where you then additionally have a very highly active market. But it's a bit hard to choose like a discrete number of states to describe this market activity level. So what we do here is we kind of follow the finance literature, and we here assume a continuous valued state process, so that we do not have discrete states, but rather a continuous valued state process. And similar approaches are indeed often used in finance. So for example, for people modeling share returns, they often use models which are called stochastic volatility models, and they also assume that the share returns there, so the Y there would be the share return, that these are driven by some kind of market nervousness, which is then also modeled with this kind of state process, which is continuous valued. So how does that look like then here in our model? So this would then be here our first like simplest state space model formulation, where we still of course assume the zero adjusted gamma distribution for the stakes. The case for pi here is a bit easier. So for pi, we simply distinguish between two cases. The pi is set to 1 if the market is closed. So what does that mean? The pi is the probability that we observe a stake equal to 0. And if this probability is 1, this means that we then observe for sure a value of 0. And this is the case if the market is closed. So because if the market is closed, no one is able to place a bet. The bookmaker closes the market. And yeah, then we simply set this probability to 1 that we observe a stake equal to 0. Otherwise, if the market is open, we simply estimate this probability here as a constant and use the log@link function to ensure that this probability is then between 0 and 1. For the mu, we assume that there's like a baseline level, so an intercept here, alpha 0, so mu has to be greater than 0. So this is why we use the exponential function here. And the intercept alpha 0 is then here, to this intercept is then added the current value of the state process, so the current value here of the underlying level of market activity, so that the mean of the betting volumes of the stakes depends on the baseline level plus the current value of the market activity level. And the market activity level then is, for this we then simply assume an AR1 process, so that the market activity level at time point t depends on the market activity level at time point t minus 1, where phi is the persistence parameter here, and we of course also have an error term here. So one drawback here of those kind of models is that if you want to fit these models, there's like no standard software package which you can use. So you have to code everything from scratch. I will not go into details here. I will just provide one reference here where this is explained, and where also our code is given here. If you want, we can of course talk about that later in more detail. Okay, some more information regarding this state process. So the phi here, the persistence parameter here in this AR1 process, which here in our case models the level of the market activity. If phi would be between -1 and 1, then we have a stationary process. And how does this process look like depending on the value for phi? So on the y-axis here, this would be the level of market activity. And if we have a value for phi close to 1, then this would mean that we have a high persistence in the market activity level, so that the market activity level stays away, so to speak, a bit more away from the 0, or a bit longer away from the 0, either on the positive or the negative side for a bit longer time. However, when the phi decreases, or when the phi is fairly small, so for example here in the bottom right, if the phi is equal to 0.05, then we observe lots of fluctuations around the 0. So here's not that much persistence in the market activity level, but if we have a larger phi, then we have more persistence in this market activity level. Okay. How does that look like then when we fit this simple model to our betting data? So fitting this model to the betting data leads to these results here. So the estimate for the parameter phi is about 0.985, which indicates that we have a very strong persistence here in the underlying market activity level. We also have a baseline level here, which is estimated as about 0.7. The estimate for gamma 0 here is -2.5. You can't but not make any sense out of these numbers when you look at this on that scale. But if you use the inverse logit function and plug in the value in this function, then you will end up with a value of about 7%, and this about perfectly mimics the value which we see or which we saw before in the sample. So this refers to the 7% of the intervals where we observe no stakes or a stake equal to 0 if the market is open. And if we compare this model to like a more baseline model where we do not have any state process, so where we do not account for this time series structure here in the data, then we see that this state space model here is highly preferred by the AIC. Okay, so coming back to the patterns we found in the data, we can now like cross out the first two. So we have incorporated that markets are closed after a goal was scored, or not only after a goal was scored, but maybe the markets are also closed if, I don't know, a penalty kick occurs or something like that. And we observe these clusters of high and low stakes. This is something which we have seen in the data, and this is accounted for by using the state space model formulation. And we have seen that with the high persistence parameter of 0.98, that we have a fairly high persistence here in the market activity level, which then leads to these clusters of rather high or rather low stakes. And you may now say, okay, is that really the case? So what we can do here is like a quick check. So what I did here is on the left, this is a plot of some actual data of the match Bayern against Stuttgart with the bets placed on Stuttgart. This match I also showed you on one of the previous slides in the beginning. And what I did here in the middle and on the right was simply to simulate data, namely from a model without a state process. So the model basically I showed you before, but where no state process is included, so we do not account for this time series structure in the data. And what we see here in the simulated data sets compared to the actual data is that we do not observe these clusters of, or these periods where we have sometimes a period with lower stakes and periods with higher stakes. This is something we do not observe here in this data if we do not account for a state process. But if we compare that to models simulated or to data simulated under a model with a state process, so with this simple state space model I showed you on the previous slide, then we see here that there are these clusters of high and low stakes, or these periods where we have sometimes a bit lower stakes and periods with higher stakes. What we see here, of course, if we compare this to the actual data, is that these don't really match right now, but this is, of course, we did not include any further covariates, so this is something which we will do up next year. So what we've seen also in the beginning is that the height of the stakes in this figure, so the amount of money which is placed on the teams, of course, depends on the quality of the teams, and also to some extent on the day of the week where the match takes place. So that's why we include here the market value on the log scale plus an interaction, and we also include dummy variables for the different days of the week here, and the reference category here are matches which are played during the week and not at the weekend. And if we fit this kind of model to the data again, we see these results. So we first see that this value of phi, so the persistence parameter for the market activity level, does not change much. We see that a higher market value increases on average the betting volumes. We see a negative effect for the market value of the opposing team. However, here we also see that the confidence interval does not include the zero. The same effect, or the same here is observed for the interaction term. And for the days of the week, we see a fairly strong negative effect here for the Saturday. This may simply because on a Saturday, not only the Bundesliga have their matches, but also many other football leagues in Europe and maybe all over the world. So there's bit more bookmakers can offer on a Saturday afternoon or a Saturday evening. So that's why we maybe observe here this negative effect. But here also for the effect of Friday on Sunday, the confidence intervals here do include the zero. And if we compare this model to the model without covariates, we see that this is clearly preferred here by the AIC. Okay, so back to our checklist here, to the patterns we observed in the data, the ones in gray, these were already captured like by the first model formulation. But now when we also include covariates for mu, for the mean, we accounted for the fact that the volumes are higher for better teams and that stakes vary with the day of the week. So there are 2 points then left here, and we will start with the second one of these. So if a match is like almost decided, then only very few bets are placed. And this is again considered here in our model formulation by the Gini coefficient. So in the predictor for, this is included then in the predictor for the pi. So the pi simply was the probability at an interval t for a stake being equal to 0. And this was set to 1 if the market is closed. And if the market is open, we simply estimate it here via this like little logistic regression model. And we include the Gini coefficient here. So the Gini was between 0 and 1, where 1 refers to situations where we have a very clear favorite, like Bayern Munich is leading by 2 goals 5 minutes before the match ends. So we would expect here a positive effect of the Gini, so that if the Gini is higher, if there's not much uncertainty about the outcome, then we would expect that we observe not that many bets. And we also counted here, or we included here the number of intervals which are remaining, because we see that we saw in the beginning that at the end of a match, usually the betting behavior is a bit different compared to the beginning of the match, so that we at the end of the match observe more time points where the stakes were equal to 0. That's why we include the number of remaining intervals here. Okay, so in the model formulation, we of course include all the covariates which we also included in the previous model, but now we also include covariates not only for mu, for the mean, but also for the pi, so for the probability that a stake is equal to 0, so that we observe those stakes. Here, the Gini is the estimated effect is positive, which means that is intuitively expected if there's a match which is like almost decided. So if the higher the certainty about the outcome is, the higher is the probability that we observe a stake equal to 0. On the other hand, the number of remaining intervals, so to interpret this correctly, maybe I have to recode this, because this is a bit confusing here. So these are the number of remaining intervals, and the number of remaining intervals in a match, so the time left is highest for the beginning of the match. So at the beginning of the match, it's less likely to observe a stake equal to 0 than at the end of the match. And this is quite intuitively plausible, I think. And yeah, so this model is also preferred over the model where we do not have any covariates here included for the pi. This is clearly preferred here by the AIC. Okay, so back to our checklist. Now we're almost there. So if a match is almost decided, not only very few bets are placed, but the stakes we observe, they are often fairly low. So put a bit differently here is that if a match is almost decided, like the market activity level decreases. And the market activity level, so this is something which, or why we use the state process here. So the state process should like serve for the level of the underlying market activity. And here we will include some more covariates. First of all, of course, for the uncertainty about the outcome, so that because we have seen in the previous plots in the figures in the beginning that if there's if the uncertainty about the outcome is quite high, then we see that the market activity level increases somehow. But we here also want to investigate the effects of gold, so of news here in the market on the market activity level. And to account for that, when we started including these covariates and started about thinking about how to model this, we thought that a linear effect might not be appropriate here, because here on the y-axis you see the effect on GT, so the effect on the market activity level. And what we had in mind was something like, if a goal was scored, then this market activity level is like elevated. So as you see here, and this after a few minutes after the goal was scored, then the market activity level decreases quite quickly. So we had such an effect here in mind, and that's why we use here 1 divided by the time which was so 1 divided by the time since the last goal was scored. simply to have this kind of shift here, so to have like an elevated effect on the market activity level if a goal was scored. And this effect is included then again for both teams, so one divided by the time since the last goal was scored by the team which bets we were analyzing, and one divided by the time since the last goal was scored by the opposing team. And as I said before, we of course also include the Gini coefficient here, because we expect an effect of the uncertainty about the outcome on the market activity level. And we also include a dummy variable here for the halftime, because in the data we also saw that that there's maybe a slight effect or a small effect of the halftime on the market activity level, so that the betting behavior bit increases during the halftime. Okay, so how does that look like? I mean, again, we have all the other covariates and parameters included in the model as before. And we see here indeed that we have a small but positive effect of the halftime. So during the halftime, the market activity level increases. For the uncertainty of outcome, we see a negative effect. So the more certain an outcome is, the lower is on average the market activity level. So a higher uncertainty, so put a bit differently, a higher uncertainty about the outcome increases the market activity level. The time since the last goal was scored has a positive effect here, is intuitively expected, I would say. And the time since the opposing team scored the last goal, this is estimated here negative, but the confidence interval here does include the 0. And if we compare this model to a model without any covariates for the market activity level, so for the state process GT, the model with covariates is again clearly preferred here. So up to now, we can say, okay, we're now done with our checklist here. So the patterns we observe in the data, these are now all included here in our state space modeling framework. So let me give a brief summary. So what have we learned so far? So we have seen that higher stakes are usually placed on teams who are a bit better, so who have a higher quality, a higher market value. And we have also seen that the uncertainty of outcome, that this plays a very important role here. So if the outcome is rather uncertain, then we see that more bets are placed in general, and we also see that a higher uncertainty about the outcome leads on average to a higher level of market activity. So we see here a clear and a nice effect of the uncertainty of outcome on betting behavior. And we also saw that this activity level of the market is affected if a goal is scored. Okay, so up to now, I showed you some of our data, presented you some of the results, which are quite nice so far, I guess. But what I didn't show you so far is whether our models are indeed useful. So I mean, with all these estimated effects and so on, some of them you say maybe this is plausible. For some of them you may say, no, this is not that convincing for me. But what I didn't show you is whether our models, which I showed you here, whether they are plausible. So whether they are able to fit to the data, whether they are able to mimic the patterns which we found in the data. And that's why we will now do some model checking here. So the main question is a bit of, or this is very, very similar to this very quick model check I showed you in the beginning, where I compared the state space model without covariates to a simple model without a state process. And the main question here again is our model able to mimic the actual data? And what we do here is basically the same thing which we did at the beginning. So we look at one example match here, look at the volumes which were placed in that match, and then we simulate data from the different models which are presented here, choose some kind of to compare this and to see whether these models are indeed able to mimic the actual data, or where these models really help here to explain something. And the example match I've chosen here is again the match Bayern versus Stuttgart, where we investigate here the bets on Stuttgart. So this is again the state space model without the covariates. And just as a reminder, so this is exactly the same slide I showed you couple of minutes ago here, where we have on the left the actual data. So this, of course, does not change here across the rows, but then the simulated data for the state space model and for the model without the state process. And here we see, okay, by using the state space model, we can nicely account for this time series structure for these different periods in the match where higher or lower stakes are placed. However, what we also see here in the top is that the stakes here are a bit too high, and yeah, that of course at the end of the match there are some unusual or not very plausible high stakes placed here according to our model. So up next we will compare this model to the model where we have covariates included for mu. So these were the market values and the day of the dummies for the days of the week. The actual data, of course, this does not change. The simulated data, now we see that the height here of the stakes almost, nicely mirrors the height of the stakes which we find here in the actual data. So this works very, very well. However, we of course see that here at the end of the match there are still some stakes placed which can also be fairly large, and this is not very plausible and also doesn't really fit here to the actual data set. So up next we will compare this model to the model where we include the covariates also for pi. So the covariates for pi, these were mainly the number of remaining intervals and the Gini coefficient measuring the uncertainty about the outcome. And here at the end, I mean, we have a very certain outcome. Bayern Munich, they are leading here by 2 goals, or at the end of the match even by 3 goals. So we would not expect, according to the model, any bets here. And we also see in the actual data that there are only few bets. This is also what we see here in the simulated data. However, according to this model, it's still kind of plausible that if a bet is placed, that these bets are fairly large. And this is something which is not that plausible, and which of course again also doesn't mimic the behavior here of the actual data. So finally, we will look at our final model where we have also covariates for the market activity level. And one covariate in the market activity level was also the Gini coefficient, where we've seen that if the outcome is very certain, or is rather certain, then this leads to a decreased market activity level. And here now we see that at the end of the match, there are still some bets placed, but we also see that in the actual data, and if the bets are placed, then the volumes are kind of rather low here. Of course, this does not mimic the pattern here in the real data like perfectly. For example, here, I mean, these are also just like 2 simulated sequences. We could also have a look at 100 different simulated sequences here of betting volumes. So, for example, here we see at the beginning that there are rather high volumes placed here according to our model, which we do not see in the actual data. So, of course, our model is not able to mimic like the actual data very perfectly, but the main patterns here, which we find in the data, they are captured by our model. And this is maybe the first thing here to discuss. So that these models are able, of course, not to mimic like all patterns which we find in the data. Not all patterns found in every match can be mimicked like perfectly from our models, but this works quite well so far. And especially these periods where we have like higher or lower stakes, which we see in the data, these are also captured here by our model. One thing we do not account for so far, or not fully account for, is the heterogeneity across teams. So I mean, of course, the teams are a bit different. If, for example, Bayern Munich scores a goal, the effect on the market activity level may be a bit different compared to, I don't know, if the Wolfsburg scores a goal. So these effects may differ across the 2 teams, and this is not considered here yet. So what's currently done to investigate this a bit further is that we fit models to each team separately, so that we not only have like one large model where we incorporate all data from all teams, but to check whether there are some substantial differences across teams. First step here is simply for us to fit these models to each team separately to check, for example, if some kinds of effects differ across teams. So this could be, as I said before, maybe the effect of a goal which is scored, that this effect is different for Bayern Munich than for some other team. This could also be included here by using some interaction effects, of course. And yeah, once this is done, so the main goal at the end of this project is to use these models, which we will hopefully then have developed then to use that these models are used for fraud detection. So how can that happen, or how can that be used? So for example, this would be a bit similar to these simulated sequences I've showed you for model checking. So if we have like a very good model which captures like all effects and which is really able to mimic the actual data, then this model could be used for forecasting, so that we then have, on the one hand, a time series of stakes placed which were indeed placed. So we have the actual data on the one hand, and then we can simulate data from our model, similar to the previous slides for model where we did the model check, and then simply compare the simulated data from our model to the actual stakes placed at the bookmaker. And if there is, for example, some period where our model would not expect a high betting volume, and in the actual data we then observe a high betting volume, this could be first indicator then for fraud. So that's how we plan to use these models for fraud detection. But this is clearly a point for future research. This has not been tackled so far. And when it comes to fraud detection and especially to prediction, then the variable selection will become way more important, because right now we just included some effects and checked whether, or we included some covariates and checked whether there is an effect, or positive or negative effect, or maybe no effect. But when we use these models for forecasting, then the variable selection issue then becomes more important. And yeah, this is something we will investigate then in future research. Okay, so up to now, this was all I wanted to talk about today. Here are then some references, and yeah, thanks for listening, and I'm happy to take your questions and comments.
Thank you very much, Marius. Really very interesting topic. I think my echo's gone now. Fantastic. Okay, there was one comment in the chat whilst you were talking, which was mainly a comment on one of your plots about the Bayer Leverkusen and Augsburg match.
Oh yeah, I will simply go to that.
Where it looked like there was a bit of activity in advance of the goal, and the question was whether that was due to trading based on a penalty decision, perhaps. I don't know if you can comment on that.
Actually, I don't know whether this was a penalty kick here or not. But so based on the comment, as far as I understood this correctly, so this would of course be very interesting to see, like in general, if the betting behavior here, of if the betting volumes tend to increase before a goal was scored. So if like the betting market can anticipate whether a goal was scored or not. So maybe this was here a penalty kick. Unfortunately, I don't know that. But this would be a very interesting research question here, which one could to some extent investigate with this data, I think. Yeah, thanks.
Cool. Thanks, Marius. And Georgios Dalbantis says it may be that Gini accounts also for the attractiveness of the betting odds. It is more attractive to place a bet when you can double your money, typically in games where both teams have a fairly equal chance of winning, than to bet on an outcome where you make a profit of only 10%, e.g. you bet on the favourite.
Okay, so the question is whether the Gini coefficient also like somehow accounts for the attractiveness of a bet.
I think so. Yeah, the idea that you might place more bets for games where it's 50-50 versus games where it's 90-10 in terms of probability of outcomes.
Yeah, of course. So I think that's that's a good point. And actually, we are still. I mean, all the stuff I presented today. So this is pretty much work in progress here. So we're still working working on that here all the time. And for the Gini coefficient, it was not that clear to us at first how to include this. So I mean, the Gini coefficient could this could also be modeled like in relation to the Gini coefficient at the beginning of the match. So for example, if we see like a kind of surprise, so if there's at the beginning of the match a high Gini coefficient, for example, if Bayern Munich plays against Augsburg, and then there's at some point maybe Augsburg scores 2 goals or something like that, and then the Gini coefficient is of course different. So that was something we also investigated, whether this could be taken into account, like not only the Gini, but also the Gini compared to the Gini coefficient at the beginning of the match, so at the kickoff. Yeah, I guess we have to look into some more details, but what I also, especially regarding the Gini coefficient here, but from the question from the chat, what I can also say here is that by now, so this is also some kind of limitation here in our model. So if I just go back to these slides where I have the Gini coefficient, so maybe here then for the state process, we included the Gini coefficient just as a linear function here. So I mean, one could, and this a bit I guess relates to the question, one could model this in a nonlinear fashion, so that for example, if the Gini is about 0, so where maybe both teams have about of the same odds, then this has a different effect than this is maybe then not linear compared to whether the Gini is then, for example, 0.5, and for a Gini close to 1, we again observe maybe a positive effect. So this is maybe not a linear effect, but maybe this is some kind of nonlinear effect here. And this is also something we have not encountered yet. But of course, this is something which is, I believe, worth looking at.
Okay, thanks, Marius. That's all the chat in the chat window. So if anyone wants to, in fact, now Rob's already got his hand up, so go ahead, Rob. Rob, we can't hear you at the moment. If you want to ask your question, Rob.
Yeah, thank you. Thanks, Marius. Really interesting stuff here. Great data. I just wondered, extending the penalty kick example that you had there from the chat. This is a period when you've got VAR, isn't it? So there are VAR decisions in your data set?
Oh, yeah, they are.
So James and I have a paper on this, but I'm just wondering if betting volumes would increase if there is a VAR intervention there, and it'd be interesting to track what sort of pattern betting volumes might take, because for the gambler you've got a decision to make. Do you actually place your bet while the VAR is deliberating, and you make second guessing the VAR, so you've got uncertainty of outcome of the call and then uncertainty of outcome of the game, because this potentially could affect the match result. So I was just wondering if you could do something on VAR.
Oh yeah, that's a great point. Thanks. Thanks very much. So at this time point here, season 2018-19, I also am quite sure that the VAR was already introduced here in the Bundesliga. And this would be very interesting to see how the betting markets react to some VAR decisions. So, I mean, given that we also have like a very precise timestamps for the halftime and for the goal. So these are also the timestamps you see here in these kind of data. These are not only the minute or some random time point during the minute where the goal was scored, but this is like a very precise time point, the exact second where the goal was scored. I believe there should also be data on the VAR, so on which second the VAR was consulted, for example, to decide on a penalty kick. So I guess that would be really interesting, how betting markets behave there if the VAR, because as you said, you have this uncertainty of outcome like twice, once on the decision and once on the penalty kick. The only thing I do not know, maybe I have to follow the betting markets there a bit next Saturday. I don't know for sure whether when the markets close, if there's a VAR decision. So for example, if there's a penalty kick, I think the markets, so at least the market for the outcome of the match, I think this is closed then, and then I'm not sure when when the market closes if a VAR decision comes in. So I would just have to check that, but that would be great to investigate, I believe.
Thanks, Marius. We've got a second hand. I can't see right now whose hand it is. I'll just Jean-Louis, do you want to ask your question?
Thanks a lot for this very clear presentation. I have two technical points to ask you. First, I do not see what is the discrepancy measure between the real data and the prediction.
So you mean these model checks here?
How you compare your predictions with the real data? What's the criterion you use?
Sorry, it was a bit hard to understand. Could you maybe repeat your question, please?
You have real data somewhere here, and you have predictions. What is the criterion you use to compare your prediction with the real data?
Yeah, well, that's measure. Okay. So, sorry. Thanks for repeating your question. So now I understand it. So that's a very good point.
Or is it overall prediction? You see what I mean?
Yeah, I think I see your point. So I think that's not that straightforward or easy to answer here. I mean, what I've showed you here is just some visual inspection where we have a look at the actual bets and on the simulated data. But one could, of course, maybe like create some summary statistics. So, for example, here in this match, we see that at the end of the match, very few bets are placed. So one could, for example, simply calculate the number of intervals where the stake was equal to 0, maybe after the second or after the third goal, and compare this to our simulated data. On average, how many intervals do we see in the simulated data where the stake is equal to 0? This could be maybe some summary statistic which we could use, or we could, for example, also add up the stakes here. So simply sum over the stakes which we see here after the second or the third goal, and compare this to the simulated data, just as a as a measure to have some quantification of that, to have some numbers, because I mean, of course you're right, but right now this is simple visual inspection, and we don't have any numbers, any summary statistics based on which we compare the actual data and the simulated data.
Because you can have an overall criterion, you can have a criterion per stage or at different time period. No?
So what kind of criterion do you mean?
No, I mean, you can have an overall criterion for all the period during the stakes are put, or you could have several criterion depending on the time period you consider. No?
Yeah, sure, of course. So sure. So we could also, I mean, the example I gave was focused on the maybe last 20 minutes of the match or something like that. But of course, we could also use summary statistics on the whole time series here, so on the complete match, where we, I don't know, maybe. So one very simple one would be simply to count or to sum the stakes here, which we see in the actual and in the simulated data, to check whether this is okay, or we sum the stakes in the halftime, or I don't know, maybe we could also sum the stakes based on 15-minute intervals or something like that. So of course these summary statistics, they do not have to focus like only very little parts of the match, but could also focus like on the whole match, or include the whole match or larger parts of the match.
And the second one is that, did you consider a training set and the test set, or do you just take the whole data set for comparing the real data and prediction?
Yeah, that's indeed also a very good point. Thanks for that. So up to now, what we've done here, so this is yeah, I mean, as I introduced it in the beginning, so here we are only interested in what kind of drivers are there for betting volumes, how does the market activity level behave, is there high persistence or not, and what kind of covariates may affect the market activity level. So here we only used the one sample, or like the whole sample to fit the model, and we do not split our model into a training and a test set. But I have to say that if we use the models for fraud detection, I mean, here we are a bit interested like in just finding some effects. We're doing some exploratory analysis. Here we fit some models, so we are here more interested in explaining something of finding some effects, whereas when it comes to fraud detection, we are then more interested not in explanation but in prediction. And then this is of course a very, very valid point, that when it comes to prediction, then we have to evaluate our models also on a test set, and cannot simply use like one sample, which is like the test and the validation set together. So then we would have to split our sample into a training and into a test set, especially when the main aim is then prediction, and this would be the case for fraud detection. So there we would consider these two different sets, a training and a test set. Yeah.
Thank you very much.
Thanks, Jean-Louis. Thanks, Marius. Next question from Dennis Coates.
Thanks, Marius. I don't know anything about this, so I probably have really stupid questions. But one thing that occurred to me as you were talking is you have the time series both on betting for one team and for betting on the other, and I don't see that you made use of those two things together. So presumably if the volume at some point betting in favor of one team spikes, something happens to the betting potentially on the other team. And I can imagine, since I don't like risk, I can imagine going in and placing a new bet on team X to win and a new bet on team Y to win to hedge my bet. And so I'm curious if there's that kind of information you might be able to use. So that's one question. The second question is it in fact that every one of these bets is placed to win? Because usually you can bet on virtually anything. You could bet on the score differential, right? And so, or you could bet on, is the team going to get a fifth goal? And those seem to be motivated very differently than just win or not win. And so do you know for a fact these are just win or not win? Is there other information you can use, or could you address?
Okay, yeah, thanks for the question. So with the I will start with the second one, if that's okay. So
that's fine.
I'm a bit sorry. Maybe I would have been better if I have explained this in a bit more detail. So these are the bets here, and also the time series which I showed here. These are always bets on a team to win. So here, for example, these in the match Bayern Munich against Stuttgart, or here Wolfsburg against Augsburg, or whatever. These are always the bets on the team to win. So these are not the bets that, I don't know, Augsburg scores at least 2 goals, or the score will be 5-0 at the end, or whatever. So these are always the bets on the team to win. I believe that there is, of course, also other data which which one could use. We don't have such data, so we have only the data on the winning team. So whether the home or away team will win, or whether the match will result in a draw. However, we have chosen here on this specific bets because this is the largest market. So I mean, you're totally right. You can bet on almost anything. You can bet on a team winning with a lead of exact 5 goals or something like that. So of course you're right. You can bet on lots of things. But this market here, where you can simply bet on the match outcome. So the home team will win, the away team will win, or the match will result in a draw. This is like the most liquid market where the most bets are placed, and that's why we've chosen to analyze this. If that answers the question, I hope.
Yes, absolutely.
Okay. And for the first question, this is indeed also a very good point here, because for this market activity level, which we include here with these and model with the state process, if I understood your first question correctly, then you may think that, okay, this does not only depend on the activity level of the team of the market. For example, I don't know, for a bet on Borussia Dortmund to win, but in the match against Bayern Munich, this would also depend then on the market activity level of the market where bets on Bayern Munich are placed, so of the opposing team. And this could indeed be included here. So then we would have not an autoregressive process of order one, but we would then have like a vector autoregressive process of order one, so that we have here the market activity level of one team, which depends on the market activity level of the own market, so to speak, plus the activity level of the market of the opposing team. And then we would have here a second line where we would have the market activity level for the other team, which then of course also depends on these two different market activity levels. And by using such a model formulation, one could, for example, then investigate the things that you suggested. So if, I don't know, if the market activity level or the betting behavior like increases in one market, does that also increase the betting volume or the market activity level in the other betting market, so that you can link these two markets? And this is right what you said. So this is considered completely separately here in our model right now. So if we look at the bets here, for example, on Borussia Dortmund and on Bayern Munich, then we consider this here as two different time series. And of course, yeah, this is a valid point that this could also be modeled jointly.
Thanks, Marius. Dennis, did you want to follow up?
No, thank you.
Great. Carl's put in the chat about the phenomenon of cashing out. I'm wondering whether Dennis was describing that when he's asking his question. And I guess that is a question, is to what extent do you know anything about the extent to which bettors are cashing out within the company that you got the data from?
So I know that there's this possibility to cash out your bet, but unfortunately we do not have any information on that. So this would also bit refer to more consumer. So more information about the specific clients here at the betting company, and we don't have any information about the clients. So we have for each second, so the black lines you see here, this is simply the only information we have. This is the sum of all bets placed in that given second, but we do not know how much money is placed by a specific individual here. So that's not contained. And I guess that's also the reason here why it's not that easy then to include the information on cash out. So we unfortunately do not have any information, although of course this would be interesting.
Because I imagine it might dictate a different pattern of betting if you plan to cash out relative to just simply wait to the end of the game, perhaps. But obviously, you know, this kind of information you don't have to hand, and I don't think anybody necessarily does, because Carl's follow-up question is whether anybody else is seeing this kind of data.
Yeah, this would be great to see, of course.
Yeah. Any more questions? Stefan.
Hi there, Marius. Very, very interesting paper. So I have a sort of I was intrigued by what you were saying near the end, where you're saying that you could use this data to somehow look at irregular patterns in the data for looking for perhaps match fixing. So I guess the sort of flippant question is, if 50,000 punters on Reddit all agreed to back a particular team, would you spot this in your data? What should be done about it? But seriously, I mean, how can you hope to identify irregular patterns in this? Do you have any thoughts about how you might do that?
Yeah, so with the first part of your question, with the people on Reddit, if they agree to bet lots of money on a certain team, then so if they all agree to place their money with the same bookmaker, then we would hopefully check or hopefully observe this pattern and identify such pattern quite quickly. Yeah, so one way one could do this is so for example, if we consider maybe just this one time series here, so it's a bit unlikely, of course, that the match fix in this match would occur in the match Borussia Dortmund against Bayern Munich. But if this would be a match, and for example, this is the actual this is the actual data, and if our simulated data or predicted data would for some intervals here maybe predict that there's, based on the course of the game, based on the dynamics, we would expect that here no bets are placed for whatever reason, maybe at the end of the match, and then we see here in the actual data that there are some stakes or higher stakes placed here. Then one could try different cutoff values. So for example, if our model now says, okay, here in the last 10 minutes of the match, our model predicts that there are, I don't know, 100 euros bet should be bet on Dortmund to win, and in the data we observe 110 euro. Then of course this would not be a huge difference. But if this difference gets larger and larger, this would be maybe a bit more of an indicator than for fraud. So one could then also some sort of standardized values, so that you use some kind of pseudo residuals or quantile residuals here, which are about standard normal distributed if the model is fine, and if we then observe very high pseudo residuals, or sometimes called quantile residuals, then this would be an indicator for fraud. So these quantile residuals, they are mostly between -3 and 3 according to the standard normal distribution, and if we would observe then values corresponding to a quantile residual of 3.5 or 4, then this would be on a kind of a standardized scale, an indicator for fraud. But in general, when we compare the stakes which are predicted by our model and the stakes which were placed indeed during a match or during some kind of period, then the larger this difference gets, the more likely then is maybe a match fix, given that we have a good model. And to check this, so we did this in a previous paper on pre-game betting markets, and there we use data on the Italian Serie B, so the second league in Italy, simply because the second league in Italy, there are several matches for which a fix has been proven, and there we could really check our models in a sense that we can check that the outliers, or the matches where our models said, okay, these were potentially fixed matches, we could then simply check with the data whether these were indeed fixed matches or not.
Yeah, I mean, I think that makes sense in the sense that, I mean, the fixing is going to be likely to be taking place in the lower divisions, in the less liquid markets, right? I mean, it's fixing the outcome of Bundesliga games seems like a very unlikely thing, generally speaking. The other question I had was how this relates to James's paper on the efficiency of markets and halftime betting. Does your data shed any light on that? Do you agree? Does it conform to James's results, or is it different? This is really a question you should have asked James, I think. But
so if I remember correctly, then in James' paper analyzing the the market efficiency right before the halftime. So these goals which were scored like I don't know, 5 minutes or closer to the halftime, they investigated the betting odds there. So this is here then of course a bit different, because we analyzed the drivers of stakes and do not focus here on the betting odds. But what I remember also from the paper from James is that they also observe a bit of a higher volume of bets here during the halftime. And we have seen down here in the results that here for our data, this is kind of confirmed, because we here we have a positive effect of the halftime, so that the market activity level is increased during the halftime. And if I remember correctly, I mean, of course, James can correct me if I'm wrong, but I think this was also one of the like side results in your paper, that that you observe higher volumes during the halftime.
That's exactly right, Marius. We wanted to check that, because we said that at halftime things should be flat, because any drift in prices after a news event, shouldn't be there if there's no news, because it's halftime. And so our contrary point would be, well, there's no betting at halftime because everyone's gone to make a cup of tea or something. But as you found, we also noted that there was just as much, if not more, betting taking place during the halftime interval. So, yep. And to answer your question, Stefan, I didn't answer because I didn't want to hog space for other more interesting questions. Speaking of which, Christina's got her hand up. So I'm going to pass over to Christina if you want to ask your question.
Thanks, and thanks, Marius. It was a really interesting presentation. Just a practical one, and feel free to not answer it, because I understand that you would put it on the future research slide. But kind of linking it back to match fixing, there's obviously a lot of match fixing data, big companies out there, Sportradar, etc., that are using already quite a lot of data analytics tools to look specifically for match fixing. So what makes your one slightly different to what's already out there?
Yeah, I guess that's for me a bit difficult to answer, because I know about Sportradar, and I know that they are doing lots of work on betting fraud detection, and that they work together with different betting companies, of course. But I don't know what kind of models they use, unfortunately. So that would be really interesting to know, of course. But from what I know, so there are some documentations on German TV. So a very recent one on match fixing, and there was like a match fixer. I mean, he was of course anonymous. And together with a journalist, he said to the journalist that he is able to fix matches, or that he knows about match fixing. And then he tells the journalist about what kind of matches he bets on, or what kind of outcomes he bets on. And then the journalist, of course, gets interested in that. And they also then went to Sportradar, so to Andreas Kranich, who's, I think, the main responsible person there for fraud detection. And it seemed like they had not all of these matches on their internal list. So basically the list of matches the journalist gave to Sportradar, there were like, I don't know, based on from 100 matches, say 99 were indeed fixed. So they are the result of these bets were as the match fixers organized it, or as they fixed it. And it seemed that Sportradar was a bit surprised by that, and so I think that they're doing, I guess, they're doing an excellent job, I believe, and they really had to detect fraud. But I mean, if our models could help to improve their models, that's something I don't know. But I expect that right now, not all match fixes are indeed uncovered by Sportradar or similar companies. But yeah, I mean, of course, I don't know whether our work could help.
No, that's brilliant. Thank you.
Thanks, Marius. Thanks, Christina. Any other questions? I might ask a quick one actually, Marius. That plot of the Dortmund Bayern game,
Yeah.
sorry.
I will go back to that.
Especially the betting on Dortmund. So, because because the different lines are goals, so I presume that it's Bayern go 1-0 up, then it's 1-0, 2-1 Bayern, then Dortmund scored twice. Is that what the different colored lines mean?
Yeah, so the red dashed line here is the goal scored by Bayern Munich, and the yellow dashed line, the goal scored by Borussia Dortmund. So Bayern scored led first by one goal, then the score was even. Bayern scored another goal, and then at the end, Borussia Dortmund scored 2 goals.
Because I'm quite intrigued by the bets placed on Dortmund versus Munich, because I would have thought that particularly once Dortmund went ahead, you'd see a flurry of activity in the Dortmund market. And I mean, it's a while since I looked at this kind of data from Betfair that we used, but you seem to spot that the betting went with the team that's that's in ascendancy, and whereas you see a lot more bets on Munich rather than Dortmund. But once it's gone 3-2 Dortmund. I don't know if you've got any comment on that at all. I mean, if that's consistent with other matches that you've got in your data set.
Yeah, this kind of also surprise was surprising for us because yeah, I mean as you said here now here with this goal the score was even again, and then we see increased betting volume here on Dortmund, but then they led they scored the winning goal, their third goal, and then the volumes here kind of decrease. So the only explanation for that I have is that maybe the odds were rather low here, so that they were not that favorable for people who wanted to bet on Borussia Dortmund. That's the best guess I have here. But yeah, I mean in the overall data set, so with all 306 matches. So for most matches, like the ones I showed on the other slides, the betting volumes mimic to some extent the dynamics of the match itself. But of course, sometimes there are also patterns like here which were kind of surprising to us. So here, my best guess would be that the odds were not that favorable for people who want to bet on Borussia Dortmund.
Yep, super. Thanks for that, Marius. I think given there's been no other questions in the time that's elapsed since I jumped in and did my host's thing and asked a question, I think we'll probably decide to draw things to a close. We're also quite close to 4 p.m. as well. So thank you very, very much, Marius, for a really interesting talk. Promoted lots of discussion. It was really interesting work, really valuable work as well, potentially with the fraud detection angle as well. So thank you very much for that. Just as I finish up, I will point us towards next week. Next week we have Nathan Ashby of the University of Texas at El Paso presenting Big Swimmer in a Small Pond or Small Swimmer in a Big Pond, Evidence of Peer Effects from High School Competition Realignments. So just as this week was the first betting talk in Voices, next week is the first swimming talk. So do join us again next week. In the meantime, have as good a weekend as you possibly can, given the restrictions that COVID continues to place on us. And I look forward to seeing you all again next week. So thank you again, Marius. Thank you, everyone, and see you again soon.
Yeah, thank you too. Bye.
Thanks, Marius. One thing to say.